Welcome back. Before the break, I had shown you 4 possible ways in which an HCl molecule can approach an ethene molecule before collision and asked you to find which of them would lead to a reaction. The correct answer is A. Why?
Because only in collision A, there is a proper orientation of ethene and hydrogen chloride molecules that lead to the formation of ethyl chloride. As a result of the collision between the two molecules, the double bond between the two carbons is converted into a single bond. The hydrogen atom gets attached to one of the carbons and the chlorine atom to the other. This can only happen if the hydrogen end of the HCl bond approaches the carbon-carbon double bond. Any other collision between the two molecules doesn't work. The two simply bounce off each other and the reaction does not take place.
Now that we know how important proper orientation is for a reaction to take place, let's see how we can relate it to the rate of a chemical reaction. This is done with the help of factor P, which is called the probability or steric factor. It takes into account the fact that in a collision, molecules which collide must be properly oriented. You must remember that its value is most often less than unity, and usually the more complex the structure of the reactant molecules, the lower is its value. Let's now go back to our virtual bowling alley.
If you recall, we had defined two parameters for a successful impact between the ball and the pin. One was the aim of the ball, which we can relate to the orientation of particles before collision. The second was the momentum of the ball, which we can now relate to the energy with which particles engage in a collision.
The minimum amount of energy required to start the reaction is called the activation energy. It is denoted by EA and is measured in joules per mole. Unless particles attain this minimum activation energy, there will be no reaction. So, we can easily say that the rate of reaction is proportional to the activation energy. Now, to make an effective collision, the molecules should have sufficient energy to break the chemical bonds in the reacting molecule. The minimum amount of energy which colliding molecules must have is known as threshold energy. Only those collisions of reactants will give products which possess energy greater than threshold energy. Here, I must remind you that once they start, different chemical reactions will have different speeds or rates at which they proceed. For example, an explosion is almost instantaneous, but the chemical reaction between iron and oxygen that leads to rusting can take a long time.
How fast a reaction proceeds depends on how frequently the collisions take place. In other words, the rate of a reaction is also proportional to the collision frequency, which is the number of collisions occurring per second per unit volume of the reaction mixture and is denoted by Z. Collision frequency increases with temperature. Higher the temperature, the larger the number of collisions will be.
Let's see how to calculate the rate of the given reaction with reactants A and B using what we have just learned.
The rate of reaction showing the relation between activation energy and collision frequency is given by equation 1, where ZAB is the collision frequency of reactants A and B. E raised to the power minus EA over RT is the fraction of molecules with energies equal to or greater than activation energy EA. R is the gas constant and T is temperature. This equation can be further modified in terms of steric factor P, which accounts for orientation of the colliding molecules as shown.
Easy, isn't it? But before we proceed, I want to make a very important point. Although collision frequency is useful for predicting the rate constants for simple reactions, it cannot predict rate constants for complex reactions involving several stages. In simple reactions, which involve only 2 or 3 molecules, the probability of the molecules orienting in the right position while colliding with the right amount of energy is more. That is, the possibility of an effective collision is more. In complex reactions, where the number of molecules reacting is more, the probability of acquiring the requisite orientation and energy is less. That is, effective collision is less. Now that we have gained so much information on collisions, let's recall the one that started off today's discussion. Well, I'm not proud of it, but it's time to talk about my minor collision in the parking lot.
If you remember, I was quite confident that there wouldn't be much damage. Why? Because I was moving at a very slow speed, so the energy involved in the impact was not enough to cause any damage.
If I had been moving at a higher speed of say 60 kilometers per hour, do you think I would have gotten away so lightly? I think not. So you see how important the role of energy is in bringing about collisions for chemical reactions to take place. Let's take a closer look at the dependence of the rate of chemical reactions on heat energy or temperature.
This dependence can be accurately explained by Arrhenius' equation, which is given by equation 2. Although it was first proposed by Dutch chemist J. H. van 't Hoff, it was the Swedish chemist Arrhenius who provided its physical justification and interpretation. Here, the reaction rate constant K is a measure of the speed of a chemical reaction, which depends on temperature. It has been found that for a chemical reaction with rise in temperature by 10 degrees Celsius, the rate constant is nearly doubled. That is, the reaction proceeds faster.
Now you know why the rate of reaction goes up if you heat the reactant mixture. Let's now take a call from a student and see what they would like to know about this topic.
We've studied in class that the collision theory fails to predict the rate constants for the reactions involving molecules with complex structures. Why is this?
I'm glad you picked up on this exception. In the collision theory, reactant molecules are assumed to be hard spheres, and the reaction is postulated to occur only when molecules collide with each other in the right orientation.
But in reality, molecules are neither spherical nor are they hard. Different molecules have different shapes, many of them quite complex.
That is why collision theory cannot correctly predict rate constant K, which is a measure of the speed of a reaction for molecules with complex structures, which often react in several stages. That brings us to the end of our theoretical discussion on collisions. I am heading straight for a break, but do join me again for exam decoded.